Good afternoon, students. So far we have been discussing the analytic functions in complex numbers. Analytic function in the sense it can be differentiated or it can be differential function at particular point. So this is called the analytic function. So we have been discussing the analytic function in complex number very well, and thereby we could prove Cauchy integral theorem, Cauchy's integral formula, and we brought out lot of properties of analytic functions. For example, analytic function in the first order or second order, third order, infinite orders. So all those things we brought up those properties. Suppose if you have analytic function, we are going to write in terms of infinite series. So we are going to have an analytic function which will be in terms of infinite series. Then we will have to think about only Taylor series. So Taylor series in which analytic function exists as infinite series. So this is what Taylor series says. Suppose if you have a complex function, the analytic function is having isolated singularity. Then we will have to go for only Laurent series. So if a complex function having an analytic function with isolated singularity, then we will have to go only for a Laurent series. So any complex wave function, any complex function that will have isolated singularity for analytic function, then we will have to go only for the Laurent series. Is it okay? So as I said earlier, Taylor series is a special case of Laurent series. So we discussed earlier. So Taylor series is a special case of Laurent series. Isolated singularity means we have any analytic function which will fail. For example, there is no analytic function at particular point z0. That's called isolated singularity. But some region the analytic function will exist. I repeat, suppose when you go for any region, particular region, or in the limit between 0 and 1, between 0 and 5, between 1 and 5, so those limits analytic function will exist, whereas analytic function will not be there at particular point z0. That's called isolated singularity. Then we will have to go only with particular series. That series will have positive powers and negative powers. That's called a Laurent series. So to put in a nutshell, a series which will have positive powers and negative powers, and that series will have analytic functions for a complex number, then we can go only for the Laurent series. So that's a N. So Taylor series will only positive numbers alone will be there. Positive power alone will be there. Whereas in Laurent series we will have positive power and negative power, and within the region. So with this introduction, we will discuss Laurent series in detail today. So Taylor series can be expressed as an infinite summation of a function, analytic function, and this summation introduces the derivatives of the function at which it can be derived. So any differentiation or derivatives exist, what we call this is Taylor series. Okay, what we call this is analytic function. On the other hand, Laurent series introduces a complex function as a power series. Laurent series or Laurent's expansion is a way to represent a complex function f of z as power series. A Laurent series is a power series representation of a complex number that includes the term with negative degrees. It's very, very important one. So in Laurent's function, we are going to deal only with positive powers also will be there, negative powers also will exist. It can be used to express complex functions when a Taylor series expansion cannot be applied. Taylor series can only be used to describe the analytic part of the function, whereas Laurent series allows us to work around the singularities of a complex function, especially the singularities, isolated singularities. It can be applied for studying the behavior of complex functions near singularities. It can be applied for studying the behavior of complex functions near singularities. So what we call this as isolated singularities. I repeat, isolated singularities means in a particular region there will be singularities. It fails to have analytic function, whereas at particular point z0 it fails. There will be analytic solution in the region. In a particular region, there will be analytic solution, whereas at a particular point, there will be no analytic function. That's called isolated singularities, used for evaluating complex integrals via the Resti theorem, Cauchy-Resti theorem. Then this can be applied for engineering level, like applied in signal processing, electronics, and control theory for stability analysis in electronic circuits and electronics. So this is the definition for Laurent series. Suppose if we consider two concentric circles, C1 and C2. So C1 and this is your C2, concentric circles. And Z modulus Z minus Z naught, which lies between R1 and R2. R1 is the radius of the first circle, R2 is the radius of the second circle. Then mod of Z minus Z naught lies between R1 and R2. Okay, where R2 is greater than R1. So that's a mistake here. R2 is greater than R1. Okay, let f of Z be analytic on R1 and R2 in the annular region. So suppose if you have any region, for example, if you take R, in between R1 and R2, you just take R, between R1 and R2. This is called the annular region. So this is annular region. Then for any point Z, any point in Z in annular region, R is given by this expression. So this is the expression for Laurent series. So there are two parts. One is the positive part, another one is a negative part. We are going to see what is the negative part, regular part and the principal part. We will differentiate. So f of Z is given by sigma n equals 0 to infinity a n Z minus a to the power n plus sigma n equals 1 to infinity b n divided by Z minus a to the power n. So this can be expanded like this. A n Z minus a to the power n plus b1 divided by Z minus a to the power n and goes on. So where a n, the expression for a n in the Laurent series is given by this expression, and bn is given by bn in the Laurent series is given by this expression. Okay, so these are all expressions. So as I said earlier, so the annular region is between two concentric circles. The series an Z minus a to the power n is called the regular part. The first part is the regular part, and second part is principal part, which will have negative power. So look over here. This is bn divided by Z minus a to the power n. I can bring this denominator to the numerator. So that will have Z minus a to the power minus n. See, minus n. So this will have negative power. So this is what I said. Laurent series will have both positive and negative series, negative powers. So this is what I explained. So this is about the negative power. Okay. So what we call this as principal part, and this what we call this as regular part. So now we'll see what is regular part, what is principal part with the small example. So f of Z is given as sin Z by Z to the power 4. Okay. So we are going to differentiate now in a Laurent series what part is regular part and what part is principal part. So that will have negative numbers. We will see. So f of Z equals sin Z divided by Z to the power 4 is not analytic at the isolated singularity Z equal to 0, and hence cannot be expanded in Maclaurin series. However, sin Z in the entire function, and we know that Maclaurin series. So we will separate now. Sin Z divided by Z to the power 4. We will separate now. First we will take the numerator. We will expand in terms of series. So sin Z is given by this series. We learnt already this series in the last video lecture. So sin Z equals, which is given by this series. Okay. Now sin Z divided by Z to the power 4 is given. Now with the series I am going to divide by 1 by Z to the power 4. I am going to divide by Z to the power 4. So this series becomes Z divided by Z to the power 4. So that will give me 1 divided by Z cube. Okay. And minus Z cube divided by 3 factorial. So that will give you minus 1 divided by 3 factorial Z. Correct? Z to the power 4 you have to divide, because as sum is given as z to the power 4. So this is z to the power 5 divided by z to the power 4, that will give you z. What is the next term? Next term is plus z divided by 5 factorial. What is the next term? Minus z cube divided by 7 factorial. See, look at these terms, first two terms. First term, the first term can be written as z to the power minus 3. Second term can be written as z to the power minus 1. See, this is negative powers, and these are all positive powers. Look over here, z cube, z to the power I, they are all positive powers. Negative powers are called principal part, positive powers are called analytic part. So this is an example of Laurent series in which principal part and analytic part exists. Okay, so small problem. Example of Taylor and Laurent series. Now we are going to have a problem in which we are going to discuss both Taylor series as well Laurent series, so that we can differentiate what's going on in Laurent series and what will be the expression for Taylor series, so we can differentiate. Now expand f of z equals 1 divided by z minus 2, z minus 3 into Taylor series as well Laurent series. So we are going to differentiate now. So the regions are given as z minus 1 lies between 0 and 1, z minus 1 lies between 1 and 2, z minus 1 is greater than 2. Okay, so you have three things are given, three regions are given. Now look over here, this is z minus 1 less than 1. Okay, this is, look, see here, 1 divided by z minus 2, z minus 3. So your 2 will be one region, then 3 will be another region. Okay, so this is your radius. So 2 will be one region, then another 3 will be another region. Your z minus 1 lies between, first inside, so inside, z minus 1 less than 1. Second one lies between 1 and 2, it lies between 1 and 2, the second region. Third one greater than 2. See, this is a picture for these expressions. Okay, now we'll solve. We'll go for first Taylor series, then after that we'll go for Laurent series. So given problem is shown here. F of z equals 1 divided by z minus 2, z minus 3. So we'll go for the first region now. Z minus 1 modulus z minus 1 lies between 0 and 1. See, f of z equals 1 divided by z minus 2, z minus 3 can be written in terms of partial fraction. We know already partial fraction. We can write this as 1a divided by z minus 3 plus b divided by z minus 2. Can you remember? Partial fraction, we are going to separate. This will be a divided by z minus 3 plus b divided by z minus 2. Okay, we have to find out the value of a and b. So your a multiplied by z minus 2 plus b multiplied by z minus 3 divided by z minus 2, z minus 3. So now you have to separate, you have to compare. So 1 equals a multiplied by z minus 2, as I said just now, plus b multiplied by z minus 3. Suppose if a equals 2, okay, suppose if a equals 2, you substitute here. A equal to means you will get minus b, this will become 0. So this will be minus b equals 1. So b equals minus 1. So your b equals minus 1. So that's why you written minus 1 here. Any doubt? Now, second one, z equals 3. Earlier z equals 2. Now, z naught will be 3. So your b will be 3. So now substitute here. Your b will be 3. So 3 minus 3 will go off. And you will get here 3 minus 2, 1. So a equals 1. So a equals 1. So this is what the partial fraction goes like this. You have a divided by z minus 3 plus b divided by z minus 2. So you will get the values of a and b using partial fraction. We know already this. Okay. Now this z minus 3 in the denominator can be written as z minus 1 minus 2. Similarly, z minus 2 can be written as z minus 1 minus 1. See, z minus 3 can be written as z minus 1 minus 2. Similarly, z minus 1 minus 1. Z minus 2 is replaced with this. Now you just change this one. Instead of z minus 1 minus 2, I am going to change into 2 minus z minus 1 with a minus sign. Can I write like this? Z minus 1 minus 2 can be written as minus of 2 minus z minus 1. I'm going to change them, right? I'm going to write this as change with a minus sign. Is it okay? Not clear. See, I'm saying this minus, see, I'm going to change this one into here and 2 here with a negative sign. I can write it. So that's why minus 1, and I can pull 2 out. So that will give me 2 in bracket. I have pulled 2 out. So 1 minus z minus 1 divided by 2. And here too, I have changed. So that will become minus sign. So that will become minus minus plus. So plus 1 divided by 1 minus z minus 1. Is it okay? So minus 1 by 2. 1 divided by 1 minus z minus 1 divided by 2 can be written in terms of series. This series is like this. Binomial series. 1 divided by, see, minus 1 by 2 I have pulled out. Remaining thing will be 1 divided by 1 minus z minus 1 divided by 2. Okay, so that will, you have to bring it to the numerator. So that will become 1 minus z minus 1 by 2 to the power minus 1. You have to write in terms of our binomial series. So the series is given by this. Similarly, 1 divided by 1 minus z minus 1. 1 minus z minus 1 can be written as 1 divided by 1 minus z minus 1 can be written in terms of our series, binomial series, exactly like this. Okay. Now, minus 2 minus 1 by 2 multiplied by 1 will be minus 1 by 2. Here 1 is there. So 1 minus 1 by 2 will give you 1 by 2. Is it okay? Minus 1 by 2, just take the first term. Here it is 1 is here. So 1 minus 1 by 2, that will give you 1 by 2. Is it okay? Now, you have to multiply this. So that will give you minus z minus 1 divided by 4. Here it is z minus 1. Here it is minus 1 by 4. Minus 1 by 4 plus 1 will give you 3 by 4. So 3 by 4 is z minus 1. Similarly, you can go for the next one. So what we call this as Taylor series. Okay, Taylor series. Now we will go for the Laurent series. For the same problem, we are going to have with the Laurent series. So f of z equals 1 divided by z minus 2, z minus 3. Okay, so z minus 1 lies between 1 and 2. 1 and 2, what we call this is annular region. So z will be lying between, see here, lying between both the circles. This is first circle, this is second circle. So your z lies between these two circles. What we call this as annular region. So modulus z minus 1 lies between 1 and 2. What out your function f of z equals 1 divided by the similar argument, but little bit we have to change. So be careful. 1 divided by z minus 2, we can write this as z minus 3 can be written as 1 divided by z minus 1 minus 2. This one. And this one we can write this as, already we have divided. See here. We have done earlier. See this is 1 divided by z minus 2, z minus 3 we have already done. We have done. So I have substituted here. This is equivalent to this. Is it okay? I repeat. See here. We have taken this function and we have already divided. We have separated. A divided by z minus 3 plus b divided by z minus 2. Already we have done. So I have written the same thing. Now, so as usual, now you are going to change and write minus 1 divided by, pull 2 out. So that will give you 2, 1 minus z minus 1 by 2. Similarly, z minus 1, you just pull it out. So that will be z minus 1, 1 minus 1 divided by z minus 1. So this can be written in terms of binomial series as this one, and 1 divided by z minus 1 I am going to keep it as it is. The remaining thing can be written as in terms of series now. See earlier we have not done, we have kept exactly 1 minus z minus 1 as it is. Earlier for Taylor series we have kept as it is 1 minus z minus 1. Now I have pulled z minus 1 out. So that will give you 1 minus 1 divided by z minus u. So now this can be written in terms of binomial series as this one. So 1 divided by z minus 1. Look at here. The power will, suppose the denominator, if it goes to the numerator, then the power will become negative principal part. This is 1 divided by z minus 1. See, here z and all in the numerator. Here z is in the denominator. If you pull numerator to the denominator to the numerator, this will become negative sign. So negative signs mean principal part. So this will be your regular part or analytic part. So both the parts, combination of both regular parts and the principal part will give you Laurent series. So this is what the difference between Taylor series and Laurent series. In Taylor series as it is written, whereas in Laurent series we have written in terms of, we have pulled z minus 1 out and we have made into series. Any doubt? Now we go for section 3, which is nothing but z minus 1 to the power, z minus 1 modulus which is greater than 2. Greater than 2. So now z is somewhere here. Okay, greater than 2. So f of z is given by the same separation, a by z minus 2 plus b by z minus 3, and we have done the same thing. Now you just pull z minus 1 out. This time there is no change here, this side. So we have pulled z minus 1 out, 1 minus 2 divided by z minus 1, and this time minus, let it be like this. You have pulled z minus 1 out, there is no change at all with the negative sign. So 1 divided by z minus 1 you have pulled, and we can write 1 divided by z minus 1 as it is. The remaining term 1 minus 2 divided by z minus 1 can be written in terms of binomial series like this, and 1 minus 1 by z minus 1 can be written in terms of binomial series like this. Okay, so this one and minus of this one will get cancelled because this is 1 by z minus 1 is common. So this one and this one will get cancelled. So remaining term, and what if 2 z minus 1 multiply this one, multiply by this one, that will be 2 divided by z minus 1 whole square. So here also you have 1 divided by z minus 1 whole square. So that will give you 2 minus 1 will give you 1. So 1 divided by z minus 1 whole square. Similarly you can go for 3, 7, goes on, other orders. So this is also Laurent series because z is in the denominator. See here, powers are in the, negative powers are there in the numerator. That's the idea. Negative powers are in the numerator. So that's why it is the Laurent series. Okay, it's a complete example for Laurent series and Taylor series. Very, very important problem. Now we will go for summary. We will go for summary results of the previous example. F of z is given as this for the 3 regions. This is the first region inside. This is the second region in between. This is the third region outside the circle. So we have obtained the series exactly like this. Okay. Any doubt? And this is for the expansion for Taylor series, and these two for Laurent series. So this is what we obtained. Okay. Now we will go for the next problem. F of z equals 1 divided by z1 plus z square. So we can find out immediately that z equals 0, 1 plus z squared equal to 0. So z squared equals minus 1. So z will be plus or minus I. Immediately we can find out the poles. See, z equals 0, z equals plus or minus I. Now in this region, that is mod of z lies between 0 and 1. First point. The second point will be mod of z is greater than that of 1. So there are 2 regions now. That is, mod of z lies between 1 and infinity. Then mod of z within 1, within unit. So both the reasons, because circle, the radius of the circle is given as 1. Now we will go for Laurent series now. The problem is given as exactly like this. Okay. So Maclaurin series representation is given by 1 divided by 1 minus z. We are going to use now. So this is given as this. So we know already this. Now for the first one, for the first region, that is mod of z lies between 0 and 1. The problem is given as 1 divided by z 1 plus z squared. See, 1 divided by z 1 divided by 1 plus z squared. Is it okay? So 1 by z 1 divided by 1 plus z squared can be written as this series z to the power minus z squared to the power n, from starting from n equal to 0 to infinity. Is it okay? This can be written as exactly like this. Now I can write this as, this will be your z to the power minus 1, correct? This will be your 1 by z, so that is z to the power minus 1. So I can write minus z2 to the power n z to the power minus 1. I repeat, 1 by z can be written as z to the power minus 1. I can combine this one and z to the power minus 1. First point. The second point is, I can pull minus, because minus z square to the power n, I can pull this minus sign, writing like this, minus 1 to the power n. So two things are there. The first thing is, you can pull this minus 1 out, minus 1 to the power n. The second one is z to the power 2n. Here one z is there, z to the power minus 1. So that will give you z to the power 2n minus 1. Is it okay? Very simple. See, this minus sign I have written like this. For all odd numbers it will be minus sign. For all even numbers it will be plus sign. Minus 1 to the power 1 minus, minus 1 to the power 2 plus, minus 1 to the power 3 minus, minus 1 to the power 4 plus. For all odd numbers it will be minus. For all even numbers it will be plus. So minus 1, that is minus 1 multiplied by z squared. So minus 1 is replaced by this, because this is to the power n. So that's why written like this. So this term can be written as exactly like this. Is it okay? Now it's given as z lies between 0 and 1. Okay, 0 and 1. Now we'll go for first n equal to 0 first. You substitute here n equal to 0. N equal to 0 means this will become 1. N equals 0 means this will become z to the power minus 1. So 1 by z. The first term is over. Plus, we'll go for the next one. N equals 1. N equals 1 means you can write exactly like this. Is it okay? Because it's given as lies between 0 and 1. So that's the reason I have separated first 0. N equals 0 first. So the second one is exactly n equals 1. Starts from n equal to 1. Already we have found out n equal to 0 here. So it starts from n equal to 1. But it's given as starting from 0 to 1. Z lies between 0 and 1. So I am going to replace n as n equal to 0. n equals 1. Instead of n equal to 1, I am going to replace this as n equals 0, because we need to have only starting from 0. So now I am going to replace n as n plus 1. I am going to replace n as n plus 1. So n will be n plus 1, which is equal to 1. So n equals 1 minus 1, n equals 0. So instead of n equals 1, I can write n equals 0. First point. And second one. So n is replaced by n plus 1. So n is replaced by n plus 1. Here n is replaced by n plus 1. So 2 n plus 1 minus 1, which is equal to 2n plus 2 minus 1, that will be 2n plus 1. So z to the power 2n minus 1 can be written as z to the power n plus 1. This 1 by z is somewhere here. So now, because the question is like this, question is starting from 0. So now this series starts from 0. Okay. Now the second one, z lies between 1 and infinity. Second one. So f of z is given as this one. So we know f of z is given, and we have done separately. We can write 1 by z cube 1 divided by 1. Just I have pulled z squared out. Here you pull z squared out. So that will give you z multiplied by z squared. Okay. So z cube 1 plus 1 divided by z squared. Is it okay? I have pulled z squared out. So that will give you 1 divided by z cube 1 plus 1 divided by z squared. So 1 divided by 1 plus z squared can be written in terms of series like this. Okay, as usual this can be written as z cube is there, z cube. So you just bring it to this side, that will give you z 2n, z to the power 2n plus 3, and this minus 1 to the power n minus 1 to the power n. Any doubt? This is z cube, you bring it to this side, this one will be z to the power 2n, so z to the power 2n plus 3. This minus 1 to the power n is ever here. Now n equals 0, starts from n equal to 0, but what out here? Starting from 1. Listen to me, it's very important problem. Okay, just understand. Starting from 1, so you have to make this n equals 0 to n equals 1. For that, what we are going to do is replace n equals n minus 1. N equals n minus 1. So n minus 1 equal to 0, so n equals 1. So now you have to replace n as n minus 1. Okay, you wait for the time being. This must be at n minus 1. Okay, wait for the time being. 2n plus 3. So 2n minus 1 plus 3, then that will give you minus 2 plus 3, that will give you 2n plus 1. So z to the power 2n plus 1. And this term minus 1 to the power n minus 1, we can write this as minus 1 to the power n minus 1 minus 1 squared. Correct? Minus 1 squared is nothing but plus 1. Correct? Minus 1 to the power 2 is nothing but plus 1. You multiply these two, will give you minus 1 to the power n plus 1. So minus 1 to the power n minus 1, here it is n minus 1, can be replaced by minus 1 to the power n plus 1. Okay, that's the reason, that's the idea.